Chapter 16 deals with solutions. Solutions are homogeneous mixtures, and solutions can be liquid solutions, which normally people think about, but they can also be gaseous solutions, like air. Air is a gaseous solution of nitrogen and oxygen. Or it can be a solid solution, like an alloy, like steel or stainless steel, or 18-karat gold. So again, solutions are homogeneous mixtures. They can be gaseous, liquid, or solid. Let's see for this slide. There are components to the solution. The major component is called the solvent. The minor component is called the solute. And those can switch depending on the ratio. So here the major component is water. So this is the solvent. The minor component is copper 2 chloride. And so what they did was they took a scoop of copper 2 chloride and dissolved it in water and formed this solution. Okay, so when we look at the solute is just this crystalline solid. It's an ionic lattice. And this is just a molecular liquid. When we form the solution here, this is what we end up doing. We end up breaking apart the solute and breaking apart the solvent to make solute solvent groups. These groups here are called hydration spheres, or hydrated ions, or solvated ions. And so if I look at the copper 2 ion here, it's positively charged. The negative end of the water molecule, that is the oxygen, will point towards it and surround it. So this ion is kind of encapsulated by water molecules, and that's called the hydration sphere. Now these water molecules aren't fixed. So for example, this water molecule can come over here and bump this one out and replace it. And but we're going to have hydrated ions. Over here we have a hydrated chloride ion. When we look at the chloride, the positive ends of the water molecules point towards it. And these are attractions here. So when the negative end of the water molecule is attracted to the ion, we call it an ion dipole attraction. Water acts as a dipole. So this is electrical attraction. And the same thing here, we form an ion dipole attraction. And so these ion dipole attractions keep the ions hydrated like that. And you can see all these hydrated ions in here. This concentrated and dilute, these are terms like, for example, you could have concentrated copper ions and use this dark blue color, or dilute. This is a reaction, this is a single relation reaction between copper wire and silver nitrate. The silver nitrate attacks the copper wire and precipitates out silver metal. Over time, the amount of silver metal grows. These are nice big crystals of silver. And the copper is attacked, that is, it's oxidized in copper 2 ions. So you can see, it's easy to see that this is more concentrated and this is more dilute here. How concentrated something can get depends on its solubility. You know, so if you really like, let's say, sugar water, can you have like infinitely concentrated sugar water? There's a limit. I mean, how many sugar cubes can you dissolve in a cup of water? Have you ever tried that? I think I did try it once, and I think I got 8 to dissolve in water, but I can't remember. It was a long time ago. Or a cup of coffee. Some things, there's a limit. Like, for example, even though sugar is very soluble, there's a limit to how much sugar will dissolve. Even though salt is very soluble, there's a limit. If you have 100 milliliters of water, do you know what that limit is? If I have 100 milliliters of water, I can only dissolve 36 grams of salt. So it depends on how salty you like your water, you know. You can't get more saltier than 36 grams per 100 milliliters. which is really salty. And so that limit is called solubility. So we have two solubilities that we use. We use one solubility to define the maximum amount that will dissolve. So for example, the solubility of sugar cubes in water, 8 maybe in a cup. Or the solubility of salt, 36 grams in 100 milliliters, the maximum. Or qualitatively, you know, if it's relatively soluble, we call it soluble. If it's relatively insoluble, we call it insoluble. So that's qualitative. When we do it quantitatively, what we want to do is we want to saturate the solution. Once the solution is saturated, we can't dissolve anymore. So if I have 36 grams of salt in 100 milliliters water and I try to add 1 more gram to get 37 grams in there, it's not possible. It doesn't dissolve. It doesn't dissolve because the solution is saturated. It can't handle any more solute. Whereas if the solution is unsaturated, then I can go ahead and dump some more solute in there and get it to dissolve until I hit the saturation limit. And so solubility quantitatively is the concentration of a saturated solution. Sometimes you can get more than what's stable, and that's supersaturated. Solutions in which the concentration of the solute is greater than the normal solubility. Did I show you the video on this one? It's not hard to make supersaturated solutions for some solutes. One of the solutes that's pretty easy to make a supersaturated solution is sodium acetate.
Is that the one that crystallizes really fast? Like
Yeah.
acetate?
Right. Let's see. All right, so in that beaker, we have a solution, and that solution contains a lot of sodium acetate. In fact, more sodium acetate than is allowed. How do you do it? How do you form it? Well, the way they form this is supersaturated sodium acetate, is they have hot sodium acetate solution. In a hot sodium acetate solution, you know, you can dissolve more sodium acetate than in a cold sodium acetate solution. So they have a hot sodium acetate solution which they cool down. And when they cool it down, it becomes less and less soluble, so it should crystallize and precipitate out, but it doesn't precipitate out so easily, because to form sodium acetate crystals, the acetates, which have a funny shape. Do you know the shape of acetate? The shape of acetate's funny. It looks like this. So it has this kind of weird shape like this. And in order to form a crystal, that acetate ion has to align just perfectly so it fits in the crystal. Well, it's not so easy to do. And so what we say is it's hard to nucleate crystals. Did you see that?
Yeah, what was that?
What that is you put some sodium acetate crystals there. The sodium acetate crystals serve as seed crystals. Seed crystals serve as a template. So if there's already a template here, then the acetate can kind of align to the template and then build up from that. And so if you seed this, it'll grow much easier. Right now, the acetates and the sodiums can't quite orient in the right configuration to form a crystal. That's called nucleation. So nucleation is very difficult here. But if there's a seed crystal, it's much easier for it to nucleate. And so, let's see.
Crystals on the outside.
So yeah, so what they're going to do, there's no crystals on the outside. So with a seed crystal there, then now it's easy to form. And so that provided a template, and now all that sodium and acetate can crystallize out of solution here. This is pretty dramatic because there's a huge difference between the solubility in hot water versus the solubility in cold water. You know, all this stuff is not soluble in cold water, but if you were to heat it up, then you can dissolve it. You can see that the seed crystal is starting to get into that flask. What's that flask called? What flask is that? I turned off the audio because he called that a test tube. It's not a test tube.
Yeah, what's that called again?
What's that called again? It's not a test tube.
Flask. It's a flask.
Yeah. Starts with an E.
Erlenmeyer flask.
Erlenmeyer flask.
Erlenmeyer.
Right. So that's sodium acetate.
It's like wax.
Yeah, it is a kind of a waxy crystal. So again, it's because nucleation, it's called nucleation. Nucleation of baby crystals is difficult. There's different ways to help. Dust helps nucleation. Scratches in the glass help nucleation.
I think it's stir it.
Stir it might help, to agitate it. I think they're probably going to drop a seed crystal in there. Let's see if they do. Oops, I missed it. Okay, there. That's a seed crystal that got dropped in there. So it's not freezing, it's just precipitating out. This is at room temperature. All right.
Can you supersaturate anything?
No. Some things are very difficult to supersaturate. So for example, like if this were sodium chloride, it's extremely difficult to separate sodium chloride because chloride are just spherical. Acetates have this odd shape. So things that have odd shapes like this are easy to supersaturate because the crystals are hard to grow. The initial, the baby crystals are hard to grow. That is, they're hard to nucleate. Other things you cannot supersaturate. You cannot supersaturate something that's miscible. In fact, you can't saturate something that's miscible. Have you heard the word miscible? Miscible means infinitely soluble. And so there's no solubility limit. Like for example, methanol. Methanol in water, how much methanol can you dissolve in water? In an infinite amount. And so what's going to happen with methanol is, let's say you have 50% water, 50% methanol. You can call it 50% methanol solution. But you can go above 50% methanol. And so pretty soon it becomes more methanol and less water. So the solute solvent flips. So miscible just means infinitely soluble. There's no limit to how much you can dissolve. Immiscible means not soluble, insoluble. It doesn't dissolve in any proportion. So what's going on here?
Supersaturated.
Supersaturated. The seed crystal. Over here, they're just showing miscible and immiscible liquids. So octane and carbon tetrachloride are miscible. You can dissolve any amount in any proportion. It could be like 99% octane, 1% carbon tetrachloride, or vice versa. So these dissolve in any proportion. Whereas oil and water, they don't mix, or gasoline and water don't mix. These are immiscible. And so this brings up the solubility rules for molecular compounds. The solubility rules for molecular compounds are like dissolves like. Octane and carbon tetrachloride are both nonpolar, so they're alike in that way. Whereas water is polar, gasoline's nonpolar. Gasoline consists of a mixture of hydrocarbons like that. And so they're immiscible liquids, miscible liquids. And so let's take a look at some solubilities. Where do we find solubilities? We can find solubilities on Wikipedia. They're there. And so let's look at sodium acetate, the solubility. You can find them on Wikipedia. It's free, or you can find these in reference books. So if we look at the solubility of sodium acetate, take a look at how this solubility changes with temperature. So for example, if you look at sodium acetate around 20 degrees C, it's 123 grams. But at 162, I mean, at 100 degrees, it'd be 162, 163 grams. So we can add another 40 grams of sodium acetate at a higher temperature. And so there's a significant difference. So therefore, if we cool it down, back down to 20, and it doesn't crystallize, that is, it's having difficult nucleating, then we have 40 grams too much sodium acetate, and all that's going to come out. That's what we saw in the video. And so that is for saturated. So all these are for saturated solutions at various temperatures. That's sodium acetate. Let's take a look at what sugar. I'm kind of curious. Sugar, you know, sugar, table sugar is called sucrose. So how much sucrose can we dissolve in water? And it looks like we can dissolve 200 grams of sugar per deciliter. How much is a deciliter?
Is it like a tenth of a liter, or is it
10 liters?
10
Deci. You know, a deciliter is a tenth, so it's 100 milliliters. 200 grams of sugar at 100 milliliters. It's quite a lot. Yeah, it's quite a lot. But it's not infinite. That's sugar. Let's see salt. How much salt we can dissolve in water. Yeah, 360 grams per liter, which would be 36 grams per deciliter, 100 milliliters. So 36 grams per 100 milliliters. A cup would be about 200 milliliters, so about 72 grams of salt. 200 milliliters would be saturated. Now, it would be very hard to get this super saturated because you look at the shapes, and these shapes can easily crystallize out. And when you look at the shape, versus when you look at sodium acetate, back up. When we look at sodium acetate, this is the acetate ion shape here, but we call it the sodium acetate crystal structure. And you look at sodium acetate, and the acetates have to line up just right. You know? Like if you look at these acetates here, they have to be in this position. So you see this one's pointing to the left, this one's pointing to the right. They have to get in that perfect position to start to crystallize. So it's a lot harder than some spherical ion to crystallize out. The sodiums are in the gold here. The acetates are this. Or actually, is this acetate? Yeah, this is acetate. No, is that? Maybe not.
What's the formula for acetate?
CH3CO minus. Okay. Let's take a look at the next topic here. Well, basically this slide is saying like dissolves like polar solutes like polar solvents, non-polar solutes like non-polar solvents. But if you have polar, non-polar, they don't mix. That's what this slide's saying. That's for molecules, but we could also dissolve salts. This. When we dissolve salts, then like sodium chloride, we form hydrated ions. These are hydrated ions, Na plus Aq. These Na pluses are surrounded by water molecules, and these chlorides are surrounded by water molecules. These hydrated ions help stabilize the solution. You know, because sodium chloride itself is very stable. I mean, it has a very high melting point. You has got strong ionic bonds holding it together. Why would it dissolve? Well, one thing that helps stabilize the solution are the hydrated ions. They help stabilize it. Now, we can't dissolve an infinite amount of sodium chloride in water. There's a limit, 36 grams per 100 milliliters. Once we hit that limit, then we'll establish something called a dynamic equilibrium, which let's take a look at here. This is called the dissolving process or dissolution. When we're dissolving sodium chloride like this, what's happening is the lattice is being broken apart by the water molecules and we're forming these hydrated ions. But if we exceed the solubility, like once we saturate this, this is what happens. Once this becomes saturated, then the ions can come back here and attach. That is, if this ion comes back here and gets stuck on the crystal, then we call it crystallization. This ion can come back here and get stuck on it. And while new ions can break off. So we have two processes occurring. We have dissolving or dissolution, which is breaking the crystal apart. And then we have the ions coming back and attaching. That's called crystallization. When the dissolving or dissolution rate is equal to the crystallization rate, then no more will dissolve. And we call that a dynamic equilibrium, and the solution is saturated. So this is what it looks like here on this slide. When we put the crystals in just DI water, initially we only have dissolving. Because there are no ions, there are no hydrated ions in here. It's dissolving. As this becomes more concentrated, then the ions can come back down and strike the crystals and stick. So we get crystallization. Eventually, the solution becomes concentrated. That is, once the solution becomes saturated, then the rate of crystallization, that is ions coming back and striking and sticking, is equal to the rate of dissolution. The rate of dissolution never changes. It just depends on the temperature. The rate of crystallization changes depending on the concentration of hydrated ions you have in the solution. And so this is our dynamic equilibrium. The dynamic equilibrium means no more will dissolve. So we got 36 grams of salt in here, and no more will dissolve. However, it's dynamic. That is, dissolution never stops and crystallization never stops. It's just going around in circles. So if you look at the crystals, even though no more crystals will dissolve, you'll see the crystals are changing because old crystals are dissolving, new crystals are forming continuously. If we look at the factors that influence solubility, I'm going to skip that other slide. Like dissolves like. So for example, now we're looking at water. What likes water? Well, ethylene glycol likes water. If we look at an ethylene glycol molecule like this, it's an alcohol. And it has two alcohol groups here. And one thing about alcohol groups are capable of hydrogen bonding. And so ethylene glycol can hydrogen bond, water can hydrogen bond, they like each other. However, hydrocarbons like oil can't hydrogen bond. And so oil and water don't like each other. So now we can break this down into specific interactions. There's three specific interactions that we look at. One is the solute-solute interaction. That is the attraction of ethylene glycol with ethylene glycol with its hydrogen bonding. And then we look at the solvent-solvent attraction. Solvent-solvent attraction will be water with water. Water likes water because they both hydrogen bond. And then we look at the solute-solvent attraction. That is ethylene glycol with water. Well, ethylene glycol can hydrogen bond, water can hydrogen bond, they like each other. Versus over here, we look at the solute-solute interaction. Solute-solute interaction over here is instantaneous induced dipole, or London forces, or dispersion forces. We just have these. But when I look at water, water has that plus hydrogen bonding. And so this has dispersion, or instantaneous dipole, this has hydrogen bonding, they don't like each other. And the attraction that forms as a result, if they come together, isn't as good for water, as water prefers hydrogen bond. Over here, the solute-solute interaction are ionic bonds. Ionic bonds are very strong. The solvent-solvent interactions are hydrogen bonding. The solute-solvent interactions are ion dipole. Well, it turns out these ion dipole hydrogen ions are fairly stable, and so that helps stabilize this solution. Ion dipole can be stronger than hydrogen bonding. The reason ion dipole can be stronger than hydrogen bonding is because ion dipole is not an unusually large dipole. Ion dipole is a full charge. A full charge is better than a delta plus or a delta minus. It's a full positive or a full minus charge. So it would be much more favorable than hydrogen bonding. All right, but there are some solutes like gases. There's nothing holding the gases together here. And so when we're looking at gases acting as a solute, like CO2, well, we can force the CO2 by increasing the pressure. So the higher the pressure of the CO2, the more CO2 dissolves in the water. The lower the pressure of the CO2, the less dissolves in water. So CO2 is interesting because we see this one in carbonated beverages. So let's take a look at. Let's take a look at. Let's take a look at the Diet Coke rocket. Seen it? Video. Actually, I haven't seen this one. Have you seen the rocket car?
Oh, wait. Can we go back to the second one?
Yeah.
This one?
Yeah, I want to see what happens if he actually ate it. Oh, he better make that little wooden.
That would be a pretty mean thing to do. But in here, what gas is that inside there? CO2. And this is pure CO2, so that's 1 atmosphere of CO2. What's the pressure of CO2 in air? Well, let me take a look at the pressure of CO2 in air really quick. You know what the pressure of CO2 in air is? Well, it depends on the percentage. So let's look at the composition of air. So if I have, let's say, if I have 100 atmospheres of air, then I would have how many atmospheres of nitrogen? 78. And I'd have how many atmospheres of oxygen? 21. And 1 atmosphere of argon. And how much CO2? 0.03 atmospheres. If I had 100 atmospheres of air, but I don't normally have 100 atmospheres of air. I normally have 1 atmosphere of air. So if I have 1 atmosphere of air, then I got 0.0003 atmospheres of CO2. So this is what happens here. Oops, what happened to the... So when he removed the lid, what happened to all that CO2? It was 1 atmosphere of CO2. Now it's 0.0003 atmospheres of CO2. So there's a heck of a lot of CO2 pushing down in here. And so what do I have? Right now, what I have in here is a supersaturated CO2 solution because it's not sustainable. I don't have enough CO2 to force that much CO2 in the liquid. Most people say no, not healthy. Is that Diet Coke or regular Coke?
Diet Coke.
Coke has a lot of sugar. This would be a fun experiment for little kids. Put your mouth on it. Oh, okay, just to taste it.
Like, when did he put his mouth on it?
Rockets, Diet Coke, and Coke. Okay, now I got it. Alright, let's see if they do the Diet Coke rocket. Alright, let me get to that. Let's see the last one.
Especially now or
That was what I expected.
Alright. I think they accidentally left it.
That is like,
Alright.
dude, that is
This guy says it goes up 100 feet, so I don't know about that.
It's gonna go 30 feet in the air. It's gonna go 30. I'm sure there's 30.
Okay, no, it's here. the CO2 has the same problem. CO2 has trouble nucleating bubbles, so this is why we use boiling chips and other things to help bubbles form. Mentos is helping the bubbles nucleate. Oops, okay. Alright, let's see. Alright.
I kind of wish it went back into the
Oh, wow.
That's slow.
We should wait.
Oh, that would hurt.
Professor, do you give us permission to do this in SI?
Yeah. Go ahead.
Oh!
Alright. So again, that's supersaturated solution. So we're going from 1 atmosphere of CO2 to 0.0003 atmospheres of CO2. So there's going to be just way too much CO2 dissolved in that. And to help the bubbles nucleate, you can use Mentos or you can use other stuff to help it nucleate. Shake it, heat it, etc. That's for gas. For gases, temperature means less soluble. And so if we heat that, it's going to go flat pretty quickly. But for solid solutes, increasing temperature just increases the solubility. And so sodium acetate has one of these steep curves where we can dissolve 40 grams more worth of sodium acetate at 100 versus 20. If we look at something like sodium nitrate here, this might be a good candidate too for supersaturation. There's a huge difference between the solubility at room temperature versus the solubility at 100. Other things aren't so dramatic, like sodium chloride, very little change. And lithium sulfates actually decrease in solubility at higher temperatures. And so you just want to know the trends. For solids, the solubility generally increases with increasing temperature. All right, for doing this, solubilities are typically expressed in how many grams you can dissolve in 100 milliliters. But normally we don't write the composition that way. When we do compositions of solutions, we use either percent for fairly concentrated solutions, or ppm for dilute, or ppb for very dilute, ppt. And so percent concentration is just the mass of solute over the total mass times 100%. I usually use percent here. If it's really dilute, then we might not want to multiply by 100. We might want to multiply by a million. So we might have very little solute and lots of solution. Multiply by a million ppm or whatever. The mass of solution is the total mass. The total mass is going to be the mass of everything in there. In this case, all we have is solute and solvent. So that's the mass of everything. Okay. So this is a percent by mass composition. We don't use percent by mass composition that much, other than like acetic acid, we use it. For some other solutions, we use it. Mainly, we use something called molarity, which we already talked about. But let's see, are we out of time?
5 minutes.
5 minutes? All right, so let's do this percent by mass composition problem here. 125 grams of the solution was evaporated in dryness. 42.3 grams of solute was recovered. So this is fairly concentrated. You know, out of the 125 grams total, 42.3 grams of it was solute. So percentage makes the most sense here. What was the percentage concentration of the solution by mass? You know, if on the other hand they only got like or let's say 42.3 micrograms of solute was recovered, then we don't want to use percent. We probably use parts per million. It really depends on how much. And so the percent is going to just be the mass of component A over the total mass times 100. solute. It doesn't matter what the solute, it could be a mixture, you know, of solutes, just fine. 42.3 grams of solute divided by 125 grams total. That would be the solution times 100%. %. So we talked about percentage, parts per million, parts per billion. The only difference is, you know, when we're dealing with very low concentrations, then we want to use a bigger factor here rather than 100, like a billion, whatever. Billion. You are to prepare 250 grams of 7.00% by mass sodium carbonate solution. What mass in grams of sodium carbonate and what volume in milliliters of water do you use? And so in this particular problem, we're going to have 250 grams of sodium carbonate solution. And the solution is going to contain pure sodium carbonate, so we need to figure out how many grams of pure sodium carbonate we have and how many grams of water. There are only two components in this. Well, how much, is it 50-50 sodium carbonate? No, it's actually, we know how much. It's 7.00% by mass sodium carbonate. When we have gas mixtures, we usually do it by mole, not by mass. But when we have solution mixtures, we always do it by mass, usually. It is liquid solutions. And so what does it mean to be 7.00% by mass sodium carbonate? It means we have 7.00 out of 100. So 7.00 what out of 100 what?
Grams.
Yeah, grams. So 7.00 grams over 100 grams. Okay, so 7.00 grams of what over 100 grams of what?
Sodium carbonate.
Yeah. Okay, we're going to have 7.00 grams of pure sodium carbonate for every 100 grams of sodium carbonate solution. And so we have pure sodium carbonate and sodium carbonate mixture, which is a solution. So if we have 250 grams, let's say, well, I can figure that out. If I have 100 grams, I got 7 grams of sodium carbonate. If I have 200 grams, how many grams of sodium carbonate do I have? 14 grams. If I have 250 grams of sodium carbonate solution, then I'm going to have 14 plus 3.5, which would be 17.5 grams. So I have 17.5 grams of sodium carbonate. So this is going to be 17.5 grams of sodium carbonate, and the rest is water. So how much water is that? That's going to be 250 minus 17.5, which gives me 232.5 grams of water. That's one way of doing it. Another way of doing it is we could just do this using dimensional analysis. If we use this doing dimensional analysis, then I would do it like this. I'd start off with 250 grams of solution. They're calling it solution. I'm going to call it sodium carbonate solution. Times this as a conversion factor. That is, there's 7.00 grams of pure sodium carbonate for every 100 grams of sodium carbonate solution. And so the grams of sodium carbonate solution cancel, and that gives me pure grams of pure sodium carbonate, and this is going to come out to 17.5 grams pure sodium carbonate. So we get the 17.5 grams of pure sodium carbonate. Next, we want to figure out how many grams of water. So we have 250 grams total. And so the grams of water would be 250 grams total minus 17.5 grams of sodium carbonate. There's only two things in this mixture, sodium carbonate and water, so the rest must be water. So we figure out the grams of water. the grams of water is going to come out to 232.5. 232.5. This is going to be some round off error. We can keep this at 233. Then 233 plus 17.5 gives us 250.5, which is more than 250 that we started with. And so we get 233 grams of water, but they're not asking for grams. They want milliliters. So we know the density of water. What's the density of water? Yeah, 1.00 grams per milliliter. And therefore, 233 grams of water is the same thing as 233 milliliters of water. So we're going to have 233 milliliters of water and 17.5 grams sodium carbonate. That's going to give us 250 milliliters of solution. Okay, I'm going to stop here. But tomorrow I plan on finishing. Sorry, we're